Field effect transistors, also known as MOSFETs, are one of the most common electronic components in our circuits. They are often used in circuits as switches. Today, let's explore how MOSFETs achieve switching functions and how they are applied in circuits. This is a commonly seen N-channel MOSFET package. Here is its simplified internal structure. Let's break it down to understand. Its body is made of P-type semiconductor. Two N-type semiconductors are embedded in the P-type body. A silicon dioxide insulating layer covers the P-type semiconductor, and a metal plate sits on top of the insulating layer. The two N-type semiconductors connect to the source and drain terminals. The metal plate connects to the gate terminal. P-type and N-type semiconductors are formed by doping silicon with different valence impurities. P-type has many holes while N-type has many electrons. To simplify, red spheres represent electrons and black ones represent holes. We know that when P-type and N-type semiconductors are joined, they form a p-n junction. A p-n junction conducts electricity in only one direction. Only when a forward voltage is applied can the p-n junction conduct. If a reverse voltage is applied, the p-n junction is cut off. Now let's look again at the MOSFET model. Note that although P-type mostly contains holes, there are still a few free electrons. Inside the MOSFET, the two N-type regions and the P-type body form two reverse p-n junctions. We try applying voltage between the source and drain. But no matter how we apply it, the source and drain do not conduct. So how does the MOSFET control conduction between source and drain? That's the clever part of the MOSFET. We now apply voltage to the gate, which generates an electric field inside the MOSFET. The electric field attracts the few electrons in the P-type region toward the metal plate. When enough electrons gather near the insulating layer, the two p-n junctions disappear, and electrons can now flow smoothly between source and drain. So, a MOSFET is a voltage-controlled current device. The electron-rich area is called the N-channel. Now we remove the gate's power source, but the electric field remains and current still flows. Why is that? It's because the gate forms a capacitor-like structure inside the MOSFET. It can store electric potential energy. In other words, the gate still has an electric field. So how do we stop the electron flow? We just need to discharge the gate using a wire, then the electric field at the gate disappears, and electrons near the insulator spread back into the P-type region. The N-channel disappears and the two p-n junctions reappear, stopping current between source and drain. Next, we build a simple circuit with real components. A bulb and a battery are connected in series between the source and drain. We connect the gate to the battery's positive terminal and the bulb lights up. We disconnect the gate from the positive terminal, but the bulb still stays lit. So how do we turn off the bulb? That's right, just connect the gate to the battery's negative terminal. To remove the gate's electric field, and the bulb turns off. By now, we all understand. that the presence of the gate's electric field controls conduction between source and drain. So MOSFETs use voltage to control switching compared to traditional mechanical switches. MOSFETs can switch hundreds to hundreds of thousands of times per second. So they are widely used in circuits. It's a component every electronics enthusiast must understand. Finally, think about it. How can we use a MOSFET to control a bulb's brightness? That's a basic application of the MOSFET. Alright, see you in the next video.